And we are good to go. All right, we're recording. All right, so today's topic is variable speed heat pumps for colder climates, specifically Midwestern climates. So we'll be talking about Illinois, Northern Indiana, Southern Wisconsin type areas. I got some examples of Minnesota stuff too, because I saw there's some guys from Minnesota on there. But mainly we're talking about, the Northern Indiana, Chicagoland type area. All right, so these heat pumps we're mainly going to talk about are typically going to be smaller size heat pumps. We will talk about some bigger ones at the end. We're talking about 5-ton type heat pumps right now, split systems. Those are rated with the quote-unquote residential rating system. Let me get rid of this extra phone here. The quote-unquote residential rating system, although they are used in commercial applications as well. So we'll talk about how the rating system works for efficiency and things like that. For right now, just know that the name of the system is HSPF, Heating Seasonal Performance Factor, and we'll explain how it works. But 13 is the maximum I could find for any split system heat pumps, 13 HSPF. That's extremely high. That is 29% higher than a normal two-stage heat pump, which is a really good heat pump, and it's 68% higher than the legal minimum. So these variable speed heat pumps really are kicking butt over the traditional split system heat pumps. The other thing we're going to talk about today is dual fuel systems. So you may realize that a heat pump kind of needs to take heat from the outdoor air, and the colder it is, the harder it is to do that. It's not impossible, it's just harder. So there are scenarios where we want to combine gas furnaces with a heat pump, or maybe on a larger system, gas boilers with a heat pump, and kind of get the best of both worlds. So we'll talk about how to do that today. And we'll also explain a little bit about how variable capacity heat pumps, as well as variable capacity air conditioners for that matter, condensing units, are capable of significantly better dehumidification than traditional systems are. Traditional meaning two-stage. If you guys have questions as we go, just type them in the chat box in the bottom right-hand corner, and I'll try to answer them the best I can on the fly. All right, so in order to understand a variable speed heat pump, we first need to get everybody on the same page with understanding a heat pump. In order to understand a heat pump, we got to make sure everybody understands what an air conditioner really does. I realize everybody on this webinar is a HVAC professional and or engineer, and you should know what an air conditioner does, but it's amazing how many people don't really understand what happens. So the easiest way to think about it, and the easiest way for you to explain it to your customers in simple terms, is that an air conditioner does not make your building or your house cold. I mean, it does. That's really what happens, right? But it's not what it's doing. It's sucking heat out of your system, out of your house, right? It's a heat removal system. It's not a cold generator, if you will. I'm going to see if you guys can see this little, hopefully you can see my little spotlight red dot on the screen. Right, so up on the top here, we have a summertime condition. On the left side of that, where my red dot is, I have a condensing unit. On the right-hand side, I got a fan coil or a furnace or whatever with an evaporator coil in it. That guy's job is to suck air from my house or my building, to remove heat from that air into my refrigeration, send it to the refrigeration pipes outside where I can reject the heat to the outdoors. Generally speaking, heat moves from hot thing to cold thing. You guys probably all know that, right? Heat goes from the hot thing to the cold thing. With refrigeration and changing of pressures, we can make it do the opposite for us. I'm going to take heat from this cool building, this 75-degree room, if you will, and I'm going to dump that heat to the 95-degree outdoors. I'm going to make the heat go from the cold thing to the hot thing, right, by using refrigeration and the changing of pressures. So once you kind of understand that an air conditioner is removing heat and kind of going against the grain, removing heat from the cooler room and dumping it to the hotter outdoors, you can much better understand what a heat pump actually does. A heat pump's job is to be your air conditioner running in reverse. So he takes heat from the outside and he dumps it into your building, right? So on the left side here, maybe it's a 0-degree day. On the right side over here, maybe it's 70-degree building. I'm going to suck heat from that 0-degree outdoor air. I'm going to pump that heat through my refrigeration network, and I'm going to dump that heat into my 70-degree room to make it even warmer, right? Just like an air conditioner would have done, it's just running in reverse, right? When we do that, my evaporator coil becomes my condenser coil becomes my evaporator coil, right? So if I look at the diagram on the right-hand side of the piping network of the heat pump, over on the right side, I got my fan coil or my furnace blower running across my indoor coil, if you will, which is normally my evaporator coil when I'm in the cooling mode. When I'm in the heating mode, that indoor coil becomes my condenser coil. On the left-hand side of the diagram, I got my quote-unquote condenser fan blowing air over my condenser coil on an air conditioner. When I switch to the heating mode, that outdoor coil now becomes my evaporator coil, right? So everything is running in reverse. The main component difference is I have a reversing valve, which is right there in the center with the 3 pipes on top, 1 on the bottom. I have a reversing valve that basically just changes where I decide to send the refrigerant to, right? So instead of taking refrigerant from my my outdoor unit and sending it to my TXV, I take refrigerant from my outdoor unit and I send it to my compressor, right? And then over to my evaporator, then to my TXV, right? So instead of going to the TXV, evaporator, compressor, condenser, it goes the opposite way. It goes from the outdoor unit, which is now the evaporator, into the compressor, and then out of the compressor to the indoor unit, and then to the TXV, and then back around the loop. The whole cycle just goes in reverse from a traditional air conditioner. With that being said, the colder it gets outside, the harder and harder and harder it is for me to get heat out of the air. Now, there's always some heat in the air, right down to absolute zero, which is like, whatever, minus 273 degrees Celsius or whatever it is. So there's always some heat in the air, but the colder it is, the harder it is for me to get it. And for me to get more of it, I need to either have higher outdoor fan speeds or I need to have bigger surface areas of my outdoor coil. Give her that little arrow. All right, so some of the problems with heat pumps in the Midwestern climates over the years, they typically would blow cold air on people, and people didn't like that, right? It was warm enough air to heat your building. Believe it or not, for most buildings, if you have, let's say, at least an 8-degree difference between your discharge air temperature and your space temperature, you could probably heat most spaces unless they're, unless the wall is made out of mesh, right? But with a normal constructed wall with single pane windows, if you got at least an 8-degree delta from supply to space, you can heat it. So in a 75-degree room, if I have 83-degree discharge air, I can heat your room and maintain the temperature of the room. Now, the problem is 83-degree air blowing across my 90-degree skin feels kind of cool, right? So I would like to have warmer air if it's going to blow across me, so I don't feel that quote-unquote cold blow. Another common misconception is that heat pumps are not designed and can't be used in northern climates. That's absolutely not true. You're not going to use it in the Arctic, where it's always negative 10 degrees. But anytime I have mild conditions, meaning 20, 30, 40 degrees outside, I can use the heat pump. And in the Midwest, we always have days like that. In fact, I'll show you exactly how many we have. Another complaint is that they're too hard to service, right? Service techs get confused. Right. There's really only 2 extra components. There's a reversing valve and there's an accumulator just to kind of buffer the extra refrigerant that we have. That's really it. Everything else is really the same. There's nothing more complex than that. Some of that complexion, I believe, has come from the fact that traditionally you've had to run lots of extra wires to control all these different stages and reversing valves and things like that. Now that's not really the case. Almost all variable speed heat pumps, residentially and commercially that I can think of, all of them have communicating type controls. And it's all just going over, a 2 or 4 wire communication cable to do all the stages and all the reversing valve. There's no field wiring by the tech. So it does make it a little bit easier. There's been some concern that perhaps they're not reliable. In fact, you'll even hear some thermostat manufacturers say, oh, our thermostat has an emergency heat switch, so when your heat pump fails, you can put your electric heater on, right? There's no data that supports that heat pumps fail more than other air conditioner types, right? It's just a misconception that people have. Because of that cold blow thing, they think it's not working, but there's no reliability difference. When we talk about variable speed compression specifically, the data we have thus far is that variable speed compressors actually are probably going to last better than single and 2-stage compressors. We don't have a lot of U.S. data, but we got a lot of data from Asia where they've been using variable speed compression on small systems much longer. And generally speaking, these things last longer. When I turn any mechanical device on, fan, compressor, whatever, it heats up and cools down the metal, right? Every time I heat something up and cool it down, it expands and contracts. Well, because I have dissimilar metals inside the compressor, outside the compressor, in the coils, and all these different things, the different metals expand and contract at different rates. So the more I heat them up and the more I cool them down, generally the more likely they are to fatigue and break. If I have variable speed equipment, as you'll see in a little bit, I tend to run it continuously. And I just kind of ramp it up and down a little bit, but it's still running, and it's not turning on and off. And it's not heating up and cooling down as much. And generally, these things tend to last longer. I also don't get the initial inrush of current when I first turn on a variable speed compressor because of the inverter, which we'll explain here also. There's been some concern perhaps about the expense of installing a heat pump. A heat pump takes no more effort to install than an air conditioner. Right? It's the exact same thing, exact same piping, exact same everything. So that's another misconception. And then there's the payback scenario, that there is no payback. That may be true sometimes. It's not true other times. I'll give you specific examples of when paybacks are going to work and when there are going to be no paybacks, and you should not use a heat pump. So we'll go through that a little bit. So in regards to the cold blow thing, that's been easily solved by all the variable speed heat pump manufacturers, both residentially and commercially. There's a couple different things that can be done to mitigate that. So one thing is that when we first turn on a heat pump, right, instead of turning the indoor fan on at the same time and blowing the cold air around, what we first do is we allow the indoor coil, which is now the condenser coil if you recall, we allow that indoor coil to start heating up, and then once it gets up to temperature, then we turn on the indoor blower to run air across it. So we'll have a ramp up period of basically a minute or so. In this case, on my drawing, it's a half a minute, where I don't even have the indoor fan running. I just leave it off completely, let the coil start warming up, right? And then when I turn the fan on, I'll have a variable speed indoor fan. And I should probably mention that if you're going to use variable speed compression, you're going to end up having variable speed outdoor fans and variable speed indoor fans to make it all work. So because I have a variable speed indoor fan, I'm able to ramp that up slowly and not bring it up on too much air until the temperature starts getting higher. Right, so because of those variable speed fans, I have the ability to mitigate that cold blow when it first starts up. Right, so normally what I want to do is I want to keep the supply temperatures above 100 degrees if I can. Right, then people won't object because it won't be blowing cool air across their skin. Traditional heat pumps, when it's mild outside, mild meaning like 50, 60 degrees out, I'm able to get above 100 degrees. In this example here, I got a 105 degree discharge with a specific single stage heat pump. And then my two stage or variable speed ones, I can have a higher discharge even and still maintain control. But as it gets colder outside and I move left on this chart, it becomes harder and harder to keep the discharge air higher because I have less heat to grab from outdoors. And a traditional heat pump kind of falls off and I end up with 80-some degree discharge air, which is not good for the occupants. If I were to graph it out like I have here, let me see if I can use my little red dot again. Right, I hope you guys can see that little red dot. If I were to graph this guy out, a standard heat pump, which is in blue on here, I got outdoor temperature on the bottom, I got discharge air up the left-hand side, right? At 60 degrees out, or 62 in this case, outside, I'm starting out with 102 degree air, which is great. That's perfect for me to heat a space. As it gets cooler outside, that air temperature starts dropping off, dropping off, dropping off. By the time I get down to 35 degrees, I got 90 degree discharge air. When I'm down at 17, I got 84 degree discharge air, and people are going to bitch. Excuse me, this is an ASHRAE presentation. People are going to complain. If I got a variable speed heat pump, that's the guy in red, I'm able to maintain the same discharge air temperature all the way through. What I start doing is I slow down the indoor blower to make sure that my discharge air stays higher. Less CFM going across the same amount of refrigerant moving through the coil is going to give me a higher discharge air. So I slow down the indoor blower to keep the discharge air temperature up. Now eventually I'm going to slow down that blower to a point where I can't get the amount of BTUs that I want. Right? So then I got to start speeding that blower back up. And that's where you see over here on the left, in this particular example at 5 degrees, my discharge air temperature starts dropping off even on the variable speed because I got to speed up that indoor blower to get the BTUs I want. But in this case, in this particular heat pump example, everything above 5 degrees outside, I can make sure that nobody gets that cold blow scenario. When it drops below 5 degrees, somebody's going to have to help me out. That means an electric strip heater or a gas furnace or something like that. If there's any questions, type them in the chat box if you can, and I'll try to answer them. And what I'm also going to do while you guys are thinking about questions, I'm going to put the first poll question up for you guys. So let me grab that and pop it up on the screen here. All right, so here's our poll question. In the heating mode of a heat pump, the outdoor coil would be called the condenser, the reversing valve, the evaporator, or the heater. So go ahead and choose your answers, and I will give you guys a few seconds to do that. If you guys need the PDHs, definitely answer the questions. Preferably answer them correctly if you can. It's like 88% of you have voted, so I'll give it another 5 seconds. 5, 4, 3, 2. All right, we'll see if we can put the results up for you guys. So as you can see, hopefully you guys can see the results screen here. The majority of you guys answered correctly, which is what the outdoor coil becomes the evaporator when I'm in the heating mode. We tend to, when working with heat pumps, we tend to refer to it physically as the indoor coil and the outdoor coil because throughout the course of the discussion, it changes jobs. So it just becomes easier to say indoor and outdoor instead of condenser and evaporator, just as a point of reference. All right, that's our first poll question. Let me see if anybody typed in any questions. Daniel asks, how do you prevent freezing during heating mode at low outdoor air temperatures? So that's a great question. So as you might imagine, if the outdoor coil becomes my evaporator and there's moisture in the air outside, which there is, as I bring the surface temperature of the evaporator coil down to the dew point temperature, I'm going to start condensing that moisture out of the outdoor air. If that moisture condenses on my coil and it's below 32 degrees, obviously it's going to start frosting my coil and eventually freeze it. So all heat pumps, whether they're variable speed or not, are going to have a defrost mode to them. So what happens in a defrost mode is that I have to bring the refrigerant temperature of the outdoor coil back up above the dew point. And the way that you do that is that you reverse the valve again, change the reversing valve over, and run the system in an air conditioning mode, which means that my outdoor coil becomes the condenser again, my indoor becomes the evaporator, and I use heat from your building to defrost the coil that's outside. Right? This will happen for a couple minutes. It may happen once an hour, it may happen 3 times an hour, it may happen once a day. It really depends on the demand of the system and specifically the outdoor air temperature outside. So that's how we defrost the coil outside and keep it from freezing. In older systems, it was done on a timer, which is kind of lame. As you might imagine, running in the air conditioning mode is an energy waste because not only did I steal heat from your building that I wanted to keep, I also got to reverse everything back and reheat it back up when I go back to the other mode. So we want to avoid the defrost mode as much as possible. So nowadays we don't do it on a timer. On any of these variable speed heat pump systems we're going to talk about today, they all have intelligent enough controls where they know the saturated suction temperature of the refrigerant. They know the outdoor temperature outside. They can estimate when those things are becoming near to each other, and they can then go into defrost mode only if they absolutely have to, which reduces significantly the amount of times it does that, which improves the efficiency rating of the heat pump and obviously the actual real operating costs. The only negative to going into the defrost mode, other than a little bit of energy use, is that now I'm blowing cold air into your building. So what we do in those cases, for those couple minutes out of the hour that we go into defrost mode, we would energize the alternate heating sources as well, like say electric heaters, to temper that air back up. Or if you had a gas furnace, we'd energize the furnace to temper that air back up. That's a good question, Daniel. All right, let's go back to our presentation. If you guys have more questions, just type them in as we go along here. Let me get back over to the other screen. All right, hopefully you guys can all see my screen again. All right, so what about northern climates? We start talking about northern climates, the first thing we got to do is figure out, well, can we even use a heat pump in these climates? So specifically, I'm looking at Indiana, Illinois, and Wisconsin because that's where the majority of you guys are from on this webinar. And right now what I'm looking at is the ASHRAE Fundamentals Handbook 2013 edition and the weather data specifically on the heating side of the equation. So if you look at that table out of the book, and hopefully you guys all have these books at your office. If not, they're phenomenal. You should get them. Plus they're ASHRAE, and this is an ASHRAE webinar, so we got to promote ASHRAE stuff. You get 2 columns. You get the 99% column and the 99.6% column. Basically, the way to kind of think about that is 99% of the heating time of the year, the outdoor temperature is going to be above the temperature listed in this column. For the other column, 99.6% of the time, it's going to be above that number. Basically meaning there's a 0.4% chance that you might have an hour of the day that you drop below these temperatures. Generally, that happens at night when you don't care about heat as much anyway. Commercially, your building might be shut down. Residentially, hopefully you're under the covers, so it's not as big of a deal. So we don't really design for anything tighter than 0.4%. But if you pick either one of these columns, and let's go with the conservative one because I know that's what you guys are all going to do anyway. We'll go with the 99.6% column. If I go down to South Bend, Indiana, my design temp is 0.2, Basically, it's 0, right? So 0 degrees is what I should be designing my heating systems for in South Bend. Now, I know that in South Bend, you're going to have a day where it's -5 or -7 or -9, etc. But we don't design for those extreme hours that hardly ever happen, right? We design for the most common scenario that possibly would happen. If I'm going over on the Illinois side, if I'm in Chicago, same 0.2. If I'm at Midway Airport, which is more urban. If I go out to O'Hare Airport, which is the official weather station, it's -1.5. Where I live in Aurora, Illinois, it's -5, right? -5.6 specifically, because I'm out in the far sticks, right? So you can kind of see how these temperatures change, but these are not really extreme temperatures. This is not like we're living in northern Canada and we got to deal with -30 and -40, right? So these temperature ranges are not that cold. They're cold, and it's going to be hard for a heat pump to do its job, but it's not impossible to use a heat pump at these temperatures. The other thing is if you look at the bin hours, right? So there's, 8,760 hours in a year. If I look at all of those hours, how many hours fall into which bucket, right? So if I'm looking only at heating hours, which means I'm looking at 65 degrees outside and less, if I look at those number of hours, in South Bend, I have 6,349 hours where I'm quote-unquote in the heating mode. In Chicago, it's 6,014, right? So basically 6,000 and a little change is what I'm talking about. It's kind of depressing when you think about it. We have 8,700 hours in the year and 6,000 of them it's heating time. Why the hell do we live in this climate, right? What I want you to focus on here is look at the hours above 30, the heating hours above 30. So when is it between 30 and 65 outside? In South Bend, 4,800 hours, which is 76% of the heating hours, it is above 30 degrees outside. But look at above 20, so between 20 and 65, it's 5,900 hours, which is 93% of the hours. 93% of my heating hours, it is above 20 degrees outside. Above 20 degrees is when heat pumps can do their thing, right? And depending on the heat pump you have, maybe you use the 30-degree number, and fine, only 76% of them, I can handle it. But the variable speed heat pumps, we typically can run them to colder temperatures and get capacity. So for right now's discussion, whether you're in Chicago at 90%, South Bend at 93%, somebody was from Minnesota on here, I think. You're at 77, which is still pretty good, right? There's a lot of hours that I can operate in a quote-unquote mild outdoor air temperature where heat pumps can really kind of shine. If I look at it graphically, because some people are wired that way a little bit better, if I look at it graphically, you can see visually, if I added up all the blocks of hours throughout the year at different outdoor air temperatures, I got a lot of hours that are in that 20 to 65 range, right? The bulk of my hours, like we said, 90+% of them are in that range. I have very few hours where it's really cold, right? And the likelihood of it being -20 on a percentage basis is 0. It could happen, but it's percentage-wise, it's 0. -10, it's going to happen, what, 5, 7, 8, 10 hours out of the year. 0, it's going to happen 50 hours of the year. All of them are going to be between midnight and 4 a.m. when you don't really care that much anyway, for the most part, right? So I don't want to play the game down here. I got to be able to heat those spaces down there, but I don't want to optimize my system for that. I want to optimize my system for this middle chunk where all the action's at, all the time's at. All right. Oop, got to clear all those little squiggly lines off there. All right, so one of the things we do to accomplish this is a dual fuel system. The traditional heat pump system would use electric heat to supplement itself when it got really cold. So we'd optimize it for those 20, 30, 40, 50 degree outside temperatures. And then when it got colder than that, we would use electric strip heaters to supplement those and bring that temperature back up. The thing we do a lot now in the past 10, 15 years is we combine heat pumps with a gas burner as well. So it can be a natural gas or a propane or theoretically even an oil burner. We combine those two systems, so when it's a mild temperature, 20, 30, 40, 50 degrees outside, run the heat pump. When it's below those temperatures, say 10 degrees, 0, 15 degrees, run the gas furnace, right? Kind of get the best of both worlds. Be able to handle the heating capacity that I need and be able to be reasonably efficient when it's super cold outside. And then when it's mild outside and the heat pump can be more efficient, we'll look at doing it that way. Did have a couple questions come in. Tom asks the source for the temperature bins. I don't know if I put that on there. Hang on, let me see if it's on here. If not, I'll have to get it for you. I don't have it in the notes. I'll get it for you, Tom. And again, I'll get it to you later on today. Syed asks, since the coil reverses from the condenser to the evaporator and heat pump application, is there any issue with the air velocity, especially for the indoor coil? There's no specific issue. The biggest issues with air velocity in HVAC systems are on evaporator coils, because if the air is moving too quickly, it can blow the condensate back off the coil and into the airstream. But once the indoor coil becomes the condenser, I don't really typically have that issue. So mainly I'm controlling the velocity of the airflow to maintain a discharge temperature at that point, and I'm not concerned about any water blowing off. Additionally, I'm typically reducing the airflows in most operating modes in the heat pump, indoor airflows, so the velocity will be lower anyway. On the outdoor side, I don't really care about the velocity in terms of water blow off either, because if it blows off, it's not going into my airstream, it's going onto the ground, so I don't really care about that. All right. So depending on your utility costs at any given moment in time, and we'll analyze some real examples, the ability to have a gas furnace in combination with a electric heat pump really allows you to kind of play the game. Well, which utility is more expensive this year versus last year? And you can kind of shift things back and forth and do a better job of saving energy as the utility costs change, right? You're kind of basically, you're hedging your bet, playing both sides of it, if you will. We'll talk about some specific examples in a little bit here. All right, so one of the things we do on heat pumps is we try to find the balance point on any heat pump system. The balance point is at what outdoor air temperature. Remember, as the outdoor temperature drops, it's harder and harder for me to get more BTUs out of the air. At what outdoor air temperature can I no longer meet the load of the building? Right, I can't get enough BTUs with this particular heat pump and those outdoor air temperatures to meet the load. Right, so I want to figure out what that point is. So that way I can decide if I need a supplemental system, and if so, how big. Now in reality, what you could always do is you can keep putting in a bigger and bigger and bigger heat pump to get the heating BTUs that you want, right? If you have a cooling load of, let's say, 3 tons, and I have a heating load of 8 tons, I could put an 8-ton heat pump in and get all the heating BTUs that I could possibly want when it's minus 10 degrees outside, right? Just keep putting bigger and bigger surface areas in there, bigger and bigger coils, bigger compressors. The problem with that is once I go back to cooling mode, if I have an 8-ton condensing unit on a 3-ton peak load, there's no way in hell I'm going to be able to maintain that thing and operate it and be able to get any decent dehumidification out of it. Right? So what happens on a heat pump is I end up traditionally sizing the heat pump for the cooling load, and then when it goes into heating mode, I just kind of get what I get, and then when the temperature drops off, I don't get as much. All right? So traditionally, we would size a heat pump for the air conditioning load, and we typically would round down a little bit. So if I had a load of, 38,000 BTUs, I would put in a 36,000 BTU 3-ton air conditioner, and that's what I would do, right? When I have a variable speed piece of equipment, I can upsize it a little bit. Now, I don't want to get crazy. I don't want to put the 8-ton unit in on the 3-ton load and expect it to ramp properly, right? But instead of rounding from 38,000 BTUs down to the 3-ton, I can round it up to a 4-ton, right? And I have the ability to vary the capacity of that system, so I could still get really good dehumidification, even better than a regular system in the summertime. So the one thing that we change on variable speed heat pumps in terms of sizing compared to traditional heat pumps is I round up to the next whole size typically, assuming that my ductwork system can handle the airflow required. If it's a new system, no problem. If it's existing, you got to look at it. There's a couple different ways you figure out the balance point. I usually use a software tool to do it, but that doesn't work quite as well on the webinar. So I'm showing you the old school graphical method here. So on the bottom of this chart, you have the outdoor temperatures going on the bottom from minus 10 to 80 on the chart, and you have your building heat loss, your load, going from 0 to 80,000 BTUs at the left-hand side. And then on this particular chart, I have 4 different heat pump combinations mapped on here. The bottom one's a 2-ton, 3-ton, 4-ton, and a 5-ton heat pump on here. 5-ton cooling, heat pumps on here. And each one of them has their curve, and you can see as it gets colder outside, they drop off. It's not necessarily a straight line because the airflows are changing and things like that. The red line on a diagonal here, that's the load of my building, right? So when it is minus 10 out, this guy is a 60,000 BTU heating load. When it's 0 out, this guy's a 54,000 BTU load. When it's 50 out, he's a 18,000 BTU load, right? So I can graph that on the same graph as the outputs of those heat pumps are graphed on, and then I can pick which heat pump I want to see where the intersecting line is. If my cooling load is 3 tons, I pick this 3-ton one. I come down the line and see, okay, you know what? At 36 degrees outside, if I put this 3-ton unit in, I'm not going to be able to get enough capacity after that, right? So that means down over here, if I can even get it, this wedge is where I need to add some additional heat. Hopefully you guys can see me drawn with the little blue marker on here, right? That wedge in here, I need to have somebody help me out and heat this space. So when it's below 36, I can still use my heat pump below 36. He can still run, but I need to bring on the electric resistance to supplement him and complement him. When I'm on this side of the equation over here on the right, no problem, because I have more capacity than I need, so I don't need to do anything extra. Heat pump handles everything on the right by himself. On the left-hand side, somebody's got to help him out. Now, if I was to put the 5-ton heat pump in, clear this off. If I was to put the 5-ton heat pump in, right, then my balance point would be right here, and would be 24 degrees. Anything below 24 degrees, someone would have to help him out. Now, that's if I can handle a 5-ton heat pump for this cooling load, if it's variable enough. I want to talk about that. Clear that drawing off too. All right, so this is how it might look, right? So this is kind of a similar graph to the one I just showed you. This is more of what happens when I put a variable speed piece of equipment on here. So this graph does also go from -10 on the left to 80 degrees on the right. Up the left-hand side, it goes from 0 to 65,000 BTUs. At 65,000 BTUs, it's a -9 degree day is where this guy kind of caps out over there. This black line is the load of my building or my house, right? As the outdoor conditions change, my heat loss is different and my needs for heating BTUs change. On the graph here, I have 3 different heat pumps labeled on here. Right, this blue one that's kind of going on a nearly straight line, the light blue one, I don't know what you call it, cyan color, that's a standard 3-ton heat pump. It's a normal everyday heat pump. This red line is a variable speed 3-ton heat pump, and this blue line is a variable speed 4-ton heat pump. Right? Now the first thing you notice about these variable speed ones is they're not straight lines. Right? The standard heat pump, he's basically on, he's doing his thing, and that's it. The variable speed heat pumps, because they could change the speed of the compressor, and they could change the speed of the condenser, and they can change the speed of the indoor fan, and the metering devices, and 50 other things they can control. We're able to maintain those higher discharge temperatures and higher BTUs. There are some weird quirks that dip down in there because of the airflow that I need for a required amount of refrigerant, but for the most part, the line's a little bit more horizontal, and then eventually it does fall off. Right, but for this one, if I put the regular 3-ton in at 36 degrees outside, that's where my balance point would have been. If I put the variable speed 3-ton in, now the balance point's 28 degrees. If I put the variable speed 4-ton in, my balance point is, we'll call it 14 degrees. Right? So just by upsizing it from a 3 to a 4-ton, I can get more capacity. I'm not saying you should randomly start upsizing heat pumps, but if it's a variable speed, variable capacity piece of equipment, you have the ability to do that. Because on a mild day, you could always ramp it down. On a fixed speed piece of equipment or even a 2-stage piece of equipment, you can't do that. So do not upsize single and 2-stage heat pumps. If they're variable capacity, you can upsize them, basically one size. So this is typically what we recommend on smaller heat pumps for upsizing, assuming you have the ductwork that can do the airflow. Right? So if you got a 2 or 2.5 ton, we say put a 3-ton in. If you got a 3-ton, we say put a 4. If you got a 3.5 or bigger, we say put the 5-ton in. That's just kind of a recommended sizing if you want to maximize for heating. You don't have to do that. You can maximize for cooling, maximize your design for cooling, and that's fine too. You're just not going to get as much heating BTUs, obviously, out of it. Most variable speed heat pumps do not come in half sizes. It typically goes 2, 3, 4, 5, 6, 8, 10, 12, 16, 18, 20, 24-ton type things. Typically don't have any half sizes at all. Because of the variable capacity, you don't need to be quite as precise, if you will. Here's just another way to look at it. This is a particular manufacturer's tool that you use to kind of graph things out on a case-by-case basis. It's the same kind of thing though. It goes from -10 to 65 outdoor temperature on the bottom. BTUs up the left-hand column. The black line on an angle is the load of the building or the house. The blue line is if I put in a standard heat pump. The green line is if I put in a variable speed heat pump. But the nice thing about doing it on this tool is it kind of automatically calculates for you. Everything in this green shaded area is my additional heat pump hours that I normally would not have gotten on a traditional heat pump system, right? And then it'll tell you, well, your standard system is going to run 4,600 hours in the heat pump mode, right? And then if I do the variable speed one, he's going to run 5,600 hours. I'm getting 23% more runtime, and I'm covering 95% of the total outdoor temperature, and I'm only needing help from something else over here. So hopefully that makes some sense to everybody too. All right, poll question number 2. Let me clear the drawing. Let's open up the poll question. Number 2. All right, hopefully that's up on your screen now. So the question is, in Northwest Indiana or Chicago area, approximately what portion of the heating hours are above 20 degrees outside? Is it 10% of the hours, 25% of the hours, 60%, 90%, or 100% of the hours? So like 61% of people voted. If you have other questions you want to ask me, type them in that chat box and I will try to address them. I think I'm all caught up on the questions except for the one answer I owe Tom. All right, I'm going to close the poll in 5, 4, 3, 2. All right, so put the results on the screen for you guys. Most of you guys got it correct. Approximately 90% of the hours, it's going to be above 20 degrees outside. So I think when we looked at it, Chicago was 90%, South Bend was 93%, so you're kind of right in that range. Even the guys all the way up in Minneapolis, you're still 77% of the hours for you. So 90% was the correct answer for this particular question. All right, back to our slides. All right, so the other thing to talk about is the efficiency of these systems, and specifically talk about them as the outdoor temperature changes. So one thing you'll often see on small systems or even large systems is you'll see EER ratings for equipment. And traditionally, we've used EER, energy efficiency ratio, to rate mechanical equipment efficiencies forever, like literally since like the 50s or whatever, right? So basically, it's how much power am I consuming versus how much heating or cooling output am I getting out of something. The problem with EER is a full load scenario. It means the mechanical equipment is running at maximum capacity. It means for cooling, it's 95 degrees outside, right? For heating, it's 47 degrees outside, and it's just running maximum capacity, right? It's not a realistic representation of what happens in most climates, right? Unless you're in, whatever, Arizona or Las Vegas or something, you're not running that many hours at 95 plus degrees, right? And I didn't put Chicago on here specifically, but if you look at St. Louis, 2% of the hours, Minneapolis, 1% of the hours, right? So we're somewhere in between there here in Chicago and Northwest Indiana. Very, very few hours on the cooling side are above 95 degrees. Same thing happens on the heating. I already talked about that side of the equation. But for cooling, EER is not very exciting. We need to look at things from a part load standpoint. Specifically, once I have variable capacity equipment, whether it's a modulating gas furnace, whether it's a variable speed heat pump or air conditioner, as soon as I have modulation, those things tend to really, really shine when I ramp them down on mild days. All right, so the previous charts I showed you over here, oops, I shouldn't go back that far now. These guys were on the heating scenario, really. Now the one I'm showing you kind of is a cooling argument, if you will, that generally speaking, the vast majority of your cooling hours are not at peak either. So I don't really care about what happens at peak design day heating or design day cooling. I mean, I care because I have to be able to cover the load on those days, but I don't care from an efficiency standpoint what happens when it's 95 degrees or 0 degrees outside. Efficiency is irrelevant because it happens so infrequently. I want to know how efficient is this system going to be between 20 and 80 degrees outside. So on smaller equipment, 65,000 BTUs and less, which is what we're talking about at the moment, heat pumps are rated in both SEER and HSPF. SEER, Seasonal Energy Efficiency Ratio, is the cooling efficiency. It works just like EER, how much energy did I buy versus how much cooling output did I get, except it is a test that changes the conditions, right? So it takes into account cycling losses, it takes into account changing outdoor air temperatures and stuff like that. It's not just 95 degrees running balls to the wall. So SEER is more of a part load test, if you will. It's not a perfect test, but it's better than EER. HSPF, Heating Seasonal Performance Factor, that is the SEER of the heating, if you will, right? So traditionally, when people talked about a heat pump efficiency, they always talk about SEER, 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 SEER. Because normally, if you had a higher SEER, you had a higher HSPF, and the lower SEER was a lower HSPF, because it was all pretty much predicated on surface area of the outdoor coil and indoor coil. But now that we have variable speed equipment, those rules have kind of changed, and you have to decouple SEER and HSPF in your head and talk about them separately. In our climate, where it's cold, SEER is irrelevant, and I'll show you financially on some calculations here in a little bit that the cooling efficiency of a small system, residential like commercial, it doesn't matter at all. There's so few cooling hours relative to heating, it doesn't make a difference. The heating efficiency is where all the action's at. Now, if you're doing a downtown high-rise with a bunch of core zones and year-round cooling, okay, fine, the math is different. But for small commercial and certainly for residential, heating efficiency is most important. So when talking about a heat pump, HSPF is more interesting and exciting to us than the SEER rating. Like I mentioned, HSPF is Heating Seasonal Performance Factor. It's very similar to the SEER test, but it's for the heating side of the equation. And the SEER test is done at 95 degrees outside. The HSPF is done at 47 degrees outside. Sounds kind of like an oddball number, but the reason it evolved that way decades ago is 47 outside from the typical indoor design temperature was the same delta T as 95 to the typical indoor temperature on a cooling system. So 47 is kind of the opposite of 95 in the heating world, if you will. Because we recognize the fact that the capacity of the heat pump drops as the outdoor air temperature drops, all heat pumps are rated at two temperatures. They're rated at the 47 degree, and they're also rated at a 20 degree lower temperature, which is 17 degrees Fahrenheit. So that way you can see how the capacity is dropping off as it gets colder outside. So you really need to look at both those numbers to see if things are going to happen kind of the way you want. You should know that HSPF isn't, like I said, it's not a straight up efficiency number. It is a seasonal type number. So it does take into account cycling losses on the equipment. Turning things on and off are a penalty for HSPF. They're turning things on and off are a penalty for SEER. They're a penalty for AFUE. They're a penalty for anything that cares about part load performance. All right. So cycling losses are real. The defrost cycle, which we talked about a little bit ago, that is a penalty to me in terms of efficiency. And if I have to engage auxiliary heaters, that is a penalty to me for efficiency, right? So when it gets to be 10 degrees outside and I got to bring on some electric strip heat, that's going to drop the rating of my heat pump, right? So HSPF takes all those things into account. Sometimes you'll see it listed as the 47 number and 17. Sometimes you'll see it ECOP and HCOP. Those are the same things. There's lots of different numbers other than 47 and 17 you can rate at, but E and H are the two numbers, if you will, the two rating points that are most commonly used. So you'll see those mentioned down here. So in this particular case, the HSPF of this heat pump is 7.8, which is a legal minimum heat pump. That means at the 47 degree number, if you ran him at full load, he's approximately 3.5 COP. That's 350% efficient, right? If I drop it down to 17 degrees outside, he's 240% efficient, a 2.4 COP. So that's something that's hard for people to get their head around, is that a heat pump, just like an air conditioner, gives me more cooling and heating capacity than the amount of energy that I buy, right? When I run your air conditioner, it's 350% efficient or whatever it happens to be. For every unit of electricity I buy from the power company, I'm getting 3.5 times that many units of cooling effect. Same thing's happening on this heat pump. For every unit of electricity that I buy from the power company, I'm getting 3.5 units of heat, right? So the best furnace, the best boiler, the best gas appliance on the market is like 97, 98% efficient. That means 98% of what I buy goes into my building, 2% goes up the flue, right? If I have electric strip heat, it's basically 100% efficient. Technically, it's slightly less than that because you're losing some of it to visible light on the coil, but basically it's 100% efficient for electric strip heat at the site. Heat pumps are 250 to 350% efficient, and even when it's colder outside, and it's 10 degrees outside, it's still over 100% efficient. Heat pumps are always, always more efficient than any other heating source you have available to you. It doesn't mean it's the cheapest to run, right? Because I might have high electric costs and low gas costs, and I'll show you that in a second. But it means it's the most efficient thing that I could possibly do. I guess the only way to be more efficient than an air-cooled heat pump is to have a water-cooled heat pump. And the only more efficient than a water-cooled heat pump is to have a geothermal water-cooled heat pump, right? In all cases, those are heat pumps, though. The reason that it's more efficient is I'm not paying to burn a fuel source, right? I'm paying to move heat. A heat pump doesn't make heat. It just moves it from outside to inside, right? Whereas a furnace or a boiler makes heat. It burns the fuel and makes the heat. A heat pump just moves it from outside to inside. If I look at different SEER ratings, on the cooling side, like I said, people like to focus on SEER. It sounds exciting and everything. This is a national average, right? So if I put in a 20 SEER, which is kind of like a top-of-the-line air conditioner in your building, and actually this is a residential example, I should specify that. Instead of a 13 SEER air conditioner, it's going to save me $100 for the whole year. National average, right? That's taking into account people in Florida and Alabama that use a lot of cooling. So when we look at Chicago and Northwest Indiana and Wisconsin and Minnesota, it's even less for us. We don't save that much energy by putting in the most efficient air conditioner in the world, right? So our savings comes on the heating side. In terms of a heat pump, if I go from the legal minimum type heat pump up to the best heat pump I could possibly find, which is 13 HSPF, saving $350. So on a heat pump, the heating savings is definitely more dominant than the cooling savings. And actually that's true not just for a heat pump. Any residential or light commercial application in our climate, the heating savings is more important. When you get to big buildings and you have core interior loads, then the rules change. But for small buildings, heating is where it's at. All right, some guys want to compare variable speed heat pumps to geothermal. That comes up a lot. It's very difficult to compare these things because heat pumps are rated in HSPF for air source heat pumps. For geothermal, they're rated in COP. COP does not take into account seasonal effects. It does not take into account cycling losses. It does not take into account defrost. It does not take into account auxiliary heat. COP is just a straight up efficiency. It's the same as EER, right? Just what's my maximum efficiency when I run balls to the wall. So you cannot compare HSPF to COP directly. If you want to compare an air source heat pump to a water source heat pump, you have to use energy modeling software tools to look at the operating cost over the full hours of the year and then see which one ends up being better. I've done that in numerous cases, and with a lot of our current utility costs, a geothermal system seldom pays for itself. If you're where I'm located and it costs you $3,500 per well ton just to dig the well and backfill it, you're never going to pay off a geothermal system. If you're in a more rural area and the drilling costs are much less and you're paying $1,200 or $1,500 per ton well, then you can start making heat pumps pay off. Or if you're digging lots of wells, like in a commercial application. Some of the tools that we use to calculate efficiencies of these systems, whether it's an air source heat pump or a water source geothermal, there's different software packages out there. These are three that I've used in the past. All three of them can compare geo to air source heat pumps on a residential basis. If you want to do commercial stuff, Train Trace and Carrier HAP are good ones to use. They can compare them as well. What I'm going to use right now is a very simple tool. It's just a little web-based tool that we use with a particular manufacturer to compare different types of heat pumps. Because this is an ASHRAE presentation, I ripped all the logos and branding off of it, and we're just going to talk generically. So this tool is really quick. It's a 5-minute tool, and pretty much everything I do is a 5-minute thing because I'm lazy. So what you do on this particular tool, see if I can get my little red dot back. You put in the heating BTUs. In this case, I got 65,000, cooling 32,000. Zip code, which is my zip code where I'm sitting right now here in the Chicagoland area. I put in my natural gas cost. This particular one was a little bit older, so I had $1 in here. I'll show you what happens as the gas cost goes down. But for right now, $1. Electric, 10 cents, which is a little bit low this year. It's more like 12. But for the time I did this, $1 a therm, 10 cents a kW. I put in my base system, which is kind of like my legal minimum thing, 13 SEER with 80% efficient. And by the way, this is a residential operation, our example. I put my second choice in here, or my first upgrade, if you will. That guy is a more efficient air conditioner. Technically it's a 21 SEER air conditioner, but when you combine it with this particular furnace, it's an 18. That's a whole other argument for the marketing people we could talk about later. with a 97% furnace. So 18 SEER, 97% furnace. I'm going to save $630 a year if I put that in. It's a good thing for people. People will often make that choice and say, yeah, I want to save $600 a year. I'm going to buy a new system anyway. Let's get an efficient one. If I wanted to, I could give them a hybrid system where I have a heat pump combined with that exact same furnace, right? And in that case, you're going to save $805 a year, an extra $170 over the other system. The nice thing about this software tool is it calculates the thermal break point for me. In this case, it's 30.4 degrees. That means when it's below 30.4 degrees, this particular heat pump cannot do all the heating load by itself for this particular house. Somebody's got to help them out. In this case, the furnace is the one that's going to have to do it. It also calculates the economic break point. That means based on my utility costs of $1.10, when it gets down to 18 degrees and below, that's when the heat pump no longer financially makes sense and I should run the furnace. Right now, what I have to do in this case is set my system up to change over at 30 degrees because I got to be able to cover the BTUs. So whenever it's below 30, boom, I go to gas furnace. Above 30, boom, heat pump. The last column is a variable speed heat pump with that same exact 97% furnace. You can see in his case, his thermal break point's a little bit lower. It's 25 instead of 30. So I can run him to a little bit lower temperature because he can kind of overspeed himself a little bit on the outdoor airflow, as well as the compressor RPM to get more BTUs. The economic break point for him is a little bit higher. He didn't do quite as good on that, so I'd still be changing over at basically the same 30. But my savings is basically an extra $45. So it's probably not worth it for me to get a variable speed heat pump to save an extra $45 over this other heat pump. And you could argue maybe it's not even worth saving $200 over the straight air conditioner, right? It's a pretty close comparison. It's not a big difference. Now, I may want the variable capacity so I get better dehumidification. We'll talk about that in a second. If my utility costs are even lower for gas than they are, like they are now, 70 cents a therm, and a little higher for electric, 12 cents a therm. So this is like right now, today, you can see what happens. The heat pump doesn't even pay for itself at all. So if you have natural gas available to you at 70 cents a therm, you should be using natural gas all the time and don't even waste your time with the heat pump. Now, if gas costs go back up, then the math changes and the heat pump makes sense, right? So natural gas furnaces aren't really the big comparison point. The big ones are propane, oil, and electric. That's where heat pumps really stand out. So this is the exact same scenario with the exact same furnaces, the exact same heat pumps. All I did was change the fuel source. Right? I changed it from natural gas to propane. I used $2.50 a gallon, which is slightly higher than our current state average for the summer, but it's way lower than the $4.10 people were paying in my state back in February. Right? So it could get even worse than $2.50. $2.50 is just kind of an average deal. I can give these people, I can take out their current system, give them the best air conditioner and furnace that I can grab right here, 18 SEER with 97% furnace. They're going to save $1,200 a year. They're going to be really happy, and everyone's going to be thrilled with the saving $1,200. They lower their heating and cooling bill from $5,000 a year down to $3,800. It takes a lot of money to heat your house with propane. I could offer them a heat pump combined with that same furnace, a 17 SEER heat pump, and they're going to save $2,500, right? More than double the savings of the other system, right? They basically cut their utility bill in half from $5,000 to $2,500. That's like almost a no-brainer thing. You should automatically do that. That last column is the variable speed heat pump, and they can save another $300 there, right? So the advantage of going to the variable speed heat pump may not be purely energy savings. There's other benefits, and I'm going to talk about those in a little bit here. I look at some of those break points. The thermal break points didn't change because I went to propane, right? No difference there. The economic break points did. Now it's a negative 12-degree break point for the first heat pump, negative 66 for the second one. It basically says economically, you should never turn this heat pump off. Just keep running it forever and ever and ever. Now, because my thermal break point's at 25 degrees, I got to switch my heat pump over at that point just to get the BTUs that I need, or something close to that. Maybe I'll switch it at 23 or something. If there's any questions, type them in. If on propane, it goes back up to $4 a gallon like it was in February, which it may or may not do this year. Who knows? Now it costs a lot to heat this house. It's $7,500 to heat this house at $4 a gallon. And the savings just goes skyrocketing, right? So if I put in a heat pump in general, a two-stage good heat pump, I'm going to save them $4,000 over their current system, right? If I put in the variable speed one, I'm going to save them $4,700. So now I'm saving an additional what do you want to call it? Almost $600 by going from a two-stage nice heat pump to a variable speed better heat pump. All right, so the bigger the utility costs, financially speaking, the more and more sense this would start making. I could also upsize the heat pump a little bit. So if you notice, I got this little box over here on this software tool. And I know this is a really basic tool we're working with, but it's really quick and easy to give examples with. I got this little check box I can check. And now instead of giving me a 3-ton heat pump, it actually gave me a 4-ton heat pump. It upsized me one. It doesn't let me check that box on the 2-stage heat pump because it knows that upsizing a 2-stage heat pump is a bad idea and it'll kill you in the summertime for dehumidification. But doing it on a variable speed and going up a half or a whole size is okay. When I do that, my savings goes up to $5,800 a year, right? So they were spending $7,500. Now they're only spending $1,700. The payback is like a 2-year payback for this person's house. Oops. So I didn't upsize it here. It's $4,700. I did upsize it there. It's $5,700. Just by going up one size at $4 a gallon for propane, I save an extra $1,000 for this person's house. And look what economically it's telling me. Don't turn the heat pump off until it's minus 98 degrees. Now, I'm not going to wait that long. I have to shut it off earlier, but I can get a lot of capacity out of it until that point. Last example, electric heat. If you don't have any gas system at all and you're running electric heat, now your fuel sources are the same. Electric heater uses electric, heat pump uses electric, right? If electric heater is 10% efficient, or excuse me, 100% efficient, and the heat pump is 2, 3, or 400% efficient, heat pump's always going to win all the time, right? So I can come into this person's house. They have a 13 SEER air conditioner with electric strip heat. I give them a really good air conditioner, 18 SEER, and they're going to save $100 a year. It's not super exciting to them. For someone who's spending $4,800 a year on their utility costs, on just their heating and cooling utility costs, saving $100 a year doesn't mean anything to them. I could put in a hybrid system, a heat pump split system that has a fan coil, a heat pump, and electric resistance supplementary heat, and now they're going to save $2,700, right? They've cut their bill in more than a half. If I put the variable speed heat pump in with electric backup, and I do that little upsizing thing to go to the 4-ton, they're going to save almost $3,200. Right, so anybody who's on propane, electric, or even oil, heat pumps make a ton of sense. If you have natural gas, you got to do a little bit of math to see if it makes sense. In our climate at the moment, it probably doesn't. But if the utility costs change like they were 4 or 5 years ago, then it starts making more sense again. All right, poll question number 3. Let's pop that guy up here. And then we got a couple more minutes after that. All right, we launched that. All right, so what rating metrics are good indicators of part load efficiency? Would it be EER, COP, thermal efficiency, and combustion efficiency? Or would it be SEER, IEER, HSPF, and AFUE? Or are you sick of the acronyms? Give it a few more seconds here. All right, anybody else not voted? There's only 71% of you voted, so somebody didn't. I'm going to give it 5, 4, 3, 2. All right, most of you guys got that one right. That's a pretty easy one. Surprised nobody checked the I hate acronyms box. You guys must all need PDHs. All right, so back to our slides here. Keep on moving. On the cooling side of the equation, there's a benefit to having variable capacity compression as well. The benefit is the ability to turn down. Now, traditionally, we've always had single-stage equipment. It's either on or off. And then we started doing 2-stage equipment, right? In your brain, in your mind, you're thinking, oh, when only one stage is running, I got 50% capacity. Well, that's not actually true. Almost every 2-stage heat pump, in fact, all the ones I could find as examples, the best one was at 68% capacity with just one stage. The highest one was 80% capacity. So you think it's 50%, but really it's more like 70, 75, something like that. If I go to variable speed compression, I can ramp down, in this example, down to 40% of capacity. There's another variable speed heat pump I'm aware of that can ramp down to 25% capacity. So I get some pretty good turnedowns when I have variable speed compression versus 1 or 2-stage compression. That's going to help me out when I want to dehumidify. I can keep the evaporator coil wetter longer and dehumidify more if I run at a lower capacity. Just to give you a couple examples, very similar to what we did on the heating side. Here's a cooling example, but the load of my building goes the opposite way. It's still that black line. It goes the other direction. Right when it's 70 degrees outside, I don't need any cooling really. And then as it moves along, it's hotter and hotter outside. I need more and more BTUs. And a variable speed system can handle anything in between those guys. So what's going to happen is he's going to, let's say it's 90 degrees outside right now. He's running over here at 40,000 BTUs. As it gets colder outside, he'll start ramping down, ramping down. He'll try to follow the load line of the house, just like we do on the heating side. He'll follow the load line until I get down to some point that I can't go any lower. So in this example, my 40% minimum. And then now what I have to do is anything below, in this case, below 76 degrees, I have to shut the heat pump off and then turn it back on, off, on, off, on. But it's not off, on, going 0, 100%, 0, 100. It's going 0, 40, 0, 40, 0, 40 for these mild conditions. And these conditions, for the most part, you're not really running your air conditioner anyway in a light commercial or residential application. Same thing happens in heating. We try to track the load line. The idea is that whenever it's above a certain temperature or below a certain temperature, that this thing is running all the time. So in the wintertime, this heat pump, once it gets below like 40-some degrees, it's not going to shut off the whole year. It's going to run nonstop. Now, when you go into setback mode, okay, fine, it'll shut off for a little while and stuff like that. But when it's occupied, it's going to run the whole time. And it should run the whole time. And conceptually, your customers are going to think it uses more energy, but it's not because you're running at reduced capacity. That's a whole different argument we can talk about. On the cooling side, having that load matching ability to track the load line gives me significantly better dehumidification than cycling a system on and off. Hence, I get better comfort. If I want to do zone dampers on there, I can do that and be able to turn down to lower rates. Everything just kind of works out better for me. There are some components that are going to be different in a variable speed heat pump versus a regular heat pump versus even an air conditioner. So some of the things that you'll note, the outdoor condenser fan has to be variable speed also. We can't just change the compressor speed and not change the airflows and expect things to work. So both the indoor and the outdoor fan have to be variable speed. I'm probably going to have an inverter that drives the compressor. That's the way almost everybody does it. There are other ways to have variable capacity compressors, but an inverter-driven one is the majority of them. Sometimes that inverter will also drive the condenser fan motor. Sometimes the condenser fan motor will have its own controller. And then I have to have a reasonably efficient compressor. You'll find variable speed rotaries and you'll find variable speed scrolls on the market, both of them for different reasons. They have different advantages, if you will. So the real advantage of having a variable speed scroll is that a scroll compressor compared to a rotary, I can overspeed it more. I can run it at a higher RPM if I want to, safely run it at a higher RPM. Sam, I see your question about the inverter, and we're going to answer that in a second. I can run it at a higher RPM, and hence I can get more capacity out of it on a cold day, right? So I get better heating performance out of variable speed scrolls. The nice thing about a rotary is inherently more efficient than a scroll. There's less internal friction, so hence it saves more energy overall, right? But it doesn't really allow me to overspeed it, right? So I can typically have a better turn down range with a rotary, and I can have better efficiency with a rotary, but I can't, better cooling efficiency, but I can't really get there on the heating side. So if you're looking at a cooling only application, a variable speed rotary is probably a smarter choice, assuming everything else is equal, right? If I'm looking at a heating dominated application, a variable speed scroll might end up being the better choice, especially if my other heating choice is electric resistance or propane, then it's kind of a no-brainer. And then as I said, two-stage scroll compressors typically operate at 0%, 70%, and 100%. There's nothing in between. Whereas the rotary typically goes from 25 to 100 and everything in between, and the scroll goes from 40 to 100 and everything in between. Other things that are different in these guys, you'll have more than one TXV. You have to have a TXV upstream of each evaporator. And because you have a heat pump, you have two evaporators, one inside and one outside, depending on what mode it is, what season it is. So you have your normal TXV on the indoor side. On the outdoor side, we have a TXV, or in this case, I'm showing an electronic expansion valve, which is a TXV that we control with that same control that's controlling the inverter. So I got modulating indoor airflows, I got modulating outdoor airflows, I got modulating compressor speeds, and I got modulating expansion valves as well. There's lots of stuff that has to be coordinated. I got a charge compensator in the unit because I will have different amounts of refrigerant needed in heating and cooling mode, so the refrigerant has to be stored and buffered somewhere. I got the inverter, which we'll talk about in a second, the variable speed compressor. I typically have more sensors and controls on here, so I can babysit things a little better, and I can operate the speeds of them to get the BTUs that I want. So I don't change the speed necessarily based on what the thermostat says. The thermostat tells me how much heating it wants, and I change the speeds to get that many BTUs. And I calculate the BTUs with my outdoor temperature sensor and suction temperature sensor. And you may have some sound mufflers as well. Because you have an inverter, and I'm going to explain what an inverter does in a second, it operates at different frequencies, and one of those frequencies could have a harmonic with the building. So in some cases, you may want to put a muffler on the refrigerant line so those frequencies don't propagate their way through the building structure. There's an EXV. That's my expansion valve that meters the refrigerant in the heating mode as it goes into the outdoor coil, which is now my evaporator coil. I have a charge compensator. For the most part, just think of that as a buffering system to store a little bit of refrigerant when I switch from heating to cooling modes. I got a variable speed compressor, like we talked about. I got a pressure transducer on the suction line, and I got a temperature sensor on the suction line. That's what the expansion valve looks like. These are either modulating, or in most cases they're stepper motors. This particular one's a 600 step motor. That's basically modulating as far as I'm concerned. It's quite a few steps of control, so you get very precise control. We use the same thing on large chillers and stuff like that. Here's what an inverter typically looks like. This is just one style. There's numerous different types. But this black box, if you will, is the inverter hanging off the side of this condensing unit. And obviously there'd be a weather enclosure cover on the front of it. I took it off for the purposes of pictures here. On the back side of the inverter, you'll see in the bottom picture there's a heat sink. That guy's in the inside of the unit, and air is blowing across him. Inverters do have a lot of waste heat. An inverter, for the newbies, is the same thing as a VFD, right? So if we were doing a commercial job with a fan or a pump, we would have called it a VFD. Here we're calling it an inverter. A VFD is an inverter, right? So I take the power in, I modulate the signal, and then I control the frequency of it coming back out. This is what an inverter might look like. So in this case, it's a single-phase piece of equipment. So I have 230 volts single phase coming in. There's a converter section to the inverter. The converter's job is to convert the AC power to DC power, because once it's DC, now I can modulate it and play with it. Then the inverter section takes that DC power and converts it to three-phase pulse width modulation and sends that voltage out to my compressor. In this particular case, the compressor is a DC compressor. That is very common. If I had an AC compressor, I'd have to convert it back again. So when you put a VFD on a fan motor, right, you have a converter that converts from AC to DC, then you have the converter to modulate the signal, then you convert it back to AC and spit it out. In the case of these variable speed heat pumps, the idea is, well, why would I want to convert it again? Every time I convert it, I have heat loss and heat waste. Let's just get DC compressors and do it that way. So AC comes in from the power company, we change it to DC, we modulate the signal to the capacity we want, and we push that back out to the compressor. It's kind of what the inside of a unit might look like. It looks like a regular unit. It looks like a two-stage unit. There's not really anything abnormal or different there. I still got the reversing valve. I still got the accumulator. The only thing different is that inverter hanging on the outside. The nice thing about having the ability to turn down more on the cooling and heating side is you can also reduce the airflows more. On a normal two-stage heat pump, when I go to single stage, assuming it's 80% on my first stage, I can only turn down my airflow 20%, which makes it harder for me to control that discharge air temperature I was talking about earlier. If I got variable capacity equipment, now I can get some pretty big reductions, and depending on the outdoor temperature and the scenario I'm looking at, I could have as much as a 60% reduction in the airflow. So I can turn down the indoor blower quite a bit, which saves me energy, gives me better dehumidification, and more comfort. If I want to put zoning systems on there, having variable capacity cooling and variable capacity heating is kind of a no-brainer if I want to be able to have one or two zones calling for cooling or heating by themselves. So bigger turn downs on zoning systems is a plus. That's a 4-ton example. It's the same thing. I don't need to do that one. All right, pull question number 4, and then we got about 3 minutes after that to wrap up. Let me launch pull question number 4. All right, so what are common benefits of a variable speed compression? Check all that apply. So this is a multiple answer thing. You can have more than one answer you can check here if you wish. So first choice is lower first cost, lower operating cost, quieter sound levels, better dehumidification, or I just want it. This one's a little bit hard, I guess, because there's so many choices. All right, about 70% of the people voted. I'm going to give you another 5 seconds. 5, 4, 3, 2. All right, I'll pop that up on the screen for you guys. Pretty much every answer, well, B, C, and D are all correct. E is a preference, right? So there's no right or wrong there. A is the only wrong answer. It's probably not going to have a lower first cost than any traditional systems. But it's very likely it's going to have a lower operating cost, and certainly a lower operating cost than other heat pumps. It's going to typically be quieter because other things are ramping down. It's definitely going to have better dehumidification, and sometimes people just want stuff because it's cool. All right, last few things. Commercially, variable speed heat pumps are becoming more and more common, but you probably don't think of it that way because you're selling, designing, engineering these systems as VRF systems, and you know they're heat pumps, but you don't really think of it like that. But a VRF is nothing more than a heat pump. It's a heat pump that has multiple indoor coils, right? And I could do another 3 hours on VRF separately, and maybe someday we'll do that. But just to kind of give you a quick overview, if you're not familiar with variable refrigerant flow systems, basically you have outdoor units that are heat pumps. You can have 1, 2, or some cases 3 of them manifolded together working as a team, if you will. Each one of them has 2 or 3 compressors in it. So I got lots of compressors and capacity stages. Those compressors, at least one of them in each unit is variable speed. Sometimes all of them are variable speed. They are inverter driven like we just talked about. And they're providing refrigerant down a main central piping system that provides cooling or heating refrigerant to all the indoor units. You can have different indoor unit types. You can have ducted units. You can have ceiling cassettes. You can have high wall duct-free split tile style units. But make no mistake, these are all heat pumps. When the reversing valve flips, the outdoor unit becomes an evaporator. The indoor units become condensers. Some of them are even sold and marketed as heat pumps. Those are the 2-pipe ones, or 2-way, depending on who you're talking to. Right? They have 2 pipes going down the middle of the building. There are also 3-pipe systems that do simultaneous heating and cooling. They are still heat pumps, but they are a little bit fancier, and it's a whole other discussion. But they basically have 3 pipes, so they can provide you hot refrigerant or cold refrigerant, if you will, to each one of your individual units. And any individual unit can be an evaporator or condenser at the same time as another one in the next room is the opposite. And then the outdoor unit trims the difference. So if you want to learn more about VRF, let me know. I have other recorded webinars I can send you on that. You can learn about it, or we can do it as an ASHRAE webinar someday. In terms of the cold weather variable speed factor, which is what we're talking about today, this is what happens on VRF units, right? So on here I got 3 different lines, all with different indoor wet bulb temperatures. And for right now, I'm going to look at the 68-degree wet bulb because that's a typical design point. And it's probably, if you got 68 wet bulb, you probably got something in the low 70s for dry bulbs. That's a pretty common design point. So as you can see, the outdoor temperatures along the bottom from -10 to 60 degrees. And as I'm lowering temperature outside, I'm maintaining my capacity. The way I'm doing that is I'm speeding things up. I'm ramping up the condenser fan to bring more units of air through the outdoor unit. And I'm ramping up the compressor. And I can also change the indoor fan speeds as well as needed. So maintaining capacity, and I get to some point, in this particular unit's case, and what is this one? This one's, what is that, 8 tons maybe? When I get to like 28 degrees outside, I can no longer make enough BTUs to do all the work by myself. So what that means is that when it gets colder than that, somebody, my electric heater, my gas boiler, somebody's got to help me out in this triangle area and help supplement me. It doesn't mean I'm going to turn my heat pump off. It means I need someone to supplement me. My heat pump is probably still my most efficient choice, but if I turn on some electric strip heat to help temper up specific zones, that's what I'm going to have to do. The other thing that I could do, oops, change my mouse over. The other thing that I could do is I could size my heat pump differently, just like I did on the light commercial residential one. I can size this thing for a -10-degree day if I really want to, right? Basically, I'm going to go up a size. And on a -10-degree day, I'm going to get 100% of the BTUs that I need for my load, which is great. All the rest of the time, I'm going to have too much. I'm going to have to ramp them down. But I could do that if I wanted to. Now, in a lot of cases, we don't do that because it's not always the most cost-effective way to size a VRF system. And additionally, a lot of VRF systems are retrofit applications into existing buildings where I might already have baseboard or radiators or some other heating source. So I'm probably going to want to use those and size the heat pump for the cooling need, get as much cheap heat pump heating as I can, and then if I need to supplement with my existing heating system, I can do that. But if I really wanted to, I could oversize my heat pump to be sized for the heating mode. I could do it that way, right? And then it'll ramp down if it doesn't need to operate at those capacities. It will ramp down when it doesn't need to. Dan asks about information on VRF webinars. Yeah, I've done numerous ones over the years, Dan. I can send you a link to other ones if you want that are industry generic. They're not brand specific. They're just generic ones. Last thought, and then we're going to wrap it up, is that other heat pumps are out there. There's water source heat pumps. There's traditional non-variable speed heat pumps. And a big thing coming down the pipe is water heater heat pumps. These are not variable capacity yet. They're just on-off type things. But you're going to see a lot more of them, and you're going to see them really quick in about 6 months. The laws change, right? So the Department of Energy rules change on the efficiency of water heaters, both for gas and electric water heaters. Gas water heaters below 55 gallons starting in April have to be at least a 0.67 energy factor, which is basically an Energy Star water heater. It's damn near an Energy Star water heater. So basically the legal minimum water heater will become an Energy Star water heater. If it's more than 55 gallons, it's got to be a 0.8 energy factor, which is even more efficient, obviously. On the electric side, if it's a small one, below 55 gallons, you can continue to have electric resistance-based heat if you wish. On the bigger ones, above 55 gallons, you have to have an energy factor of 2 point something, right? Once I get above 100% efficient, which would be a 1.0 energy factor, the only thing I can do is heat pump technology. We have no other technology anywhere that I'm aware of, at least in the HVAC world, for space heating or water heating that can do more than 100% efficiency other than a heat pump. So anything bigger than 55 gallons electric fuel sourced has to be a heat pump nationally by law, no other choice. So you're going to start seeing heat pump water heaters if you haven't already started seeing them already. Just to give you a little example, like these are the smaller ones, obviously. These are 50-gallon ones on this example, but it kind of gives you a reality check nationally. These energy guide tags, if you will, are national fuel cost numbers, right? So in this case, it's $195 to run my 50-gallon heat pump water heater versus $500 to run electric resistance, $300 to run a gas one, $225 to run a tankless one, that kind of thing. Right now, our fuel costs are a little bit lower in the Midwest, so some of these numbers would change on the actual gas one, but it still gives you an idea of what it's kind of like. The way these heat pump water heater works is the same way any other heat pump works. Basically, there's an evaporator and there's a condenser, right? In this case, I'm taking air out of your building or out of your house and running that through my heat pump, and I'm stealing the heat from your house to heat my water, right? And then somebody has to make up that difference, right? And so my furnace or boiler or something's have to run a little bit more to make up the difference of the heat I'm stealing out of your house, although the amount of BTUs is really, really small. And because there's no flue up the middle of the water heater, the BTU loss out of the tank is really, really low. In the wintertime, it's a bit of a heating penalty. I don't know if it's enough to even change your load calc on a building or a house, but it's a little bit of a heating penalty from stealing that air. In the summertime, it's a bit of a credit because I'm actually dehumidifying that air, right, which helps me do a little bit less cooling work with my latent side of my cooling system. All right, final poll question, and we'll close it off here. This one just basically you can rate if I'm an idiot or not. Right? Don't pick the idiot one. If anybody has any more questions, type them in. I'll try to answer them. As far as the chapter goes, our next event is on October 16th. We have a lunch meeting in South Bend and a dinner meeting in Highland. The guys from BDR are going to come out and present, and they're going to do HVAC noise and vibration control. Right? So both how the sounds work and where they propagate from and what you can do to minimize some of those things. And hopefully you don't have anything like the picture where the back of that fan is just getting broken there by going the wrong way. Our next webinar is November 6th. The topic there is gas detection and control systems. So it'll be very similar setup to today, just a different topic. Nobody else has typed any questions in, so I'm going to go ahead and shut things down. As far as PDHs go, after we get the report from the webinar service to see who qualified for PDHs, the chapter will be sending those certificates out. And they will just say, one PDH on there. It won't say a specific state, so you can use it in Indiana, Illinois, and Wisconsin, no problem. If you want to use it in another state, you're on your own to submit it and get it approved but you can try to do that if you wish. Thank you guys for your time.